In this example, a parallel plate capacitor of capacitance C is charged up to a voltage of V. The charge stored in the capacitor is Q. The capacitor is then disconnected and from circuit, and so there's no electrical contact between the parallel plates. The distance between the plates is double, and this causes the capacitance to half. State how the following change. Okay, before we start the question, let's figure out what's going on. So we're closing the circuit here and letting the charge build up on the capacitor, and then we're going to disconnect that from the circuit and we're going to pull apart the capacitor plates, and this is causing the capacitance to half. Okay, the important part here is that the circuit's been disconnected and there's no electrical contact between the plates. This means the charge is stuck on the plates. It can't go anywhere. It can't destroy the charge. So charge Q is a constant. And then the distance between the plates is doubled. So we know D, which is lowercase d there, which is the distance between the plates, is times 2. And this is causing the capacitance to half. So capital C, capacitance is half. Okay, so to figure out what's going to have the potential difference between of the across the plate, I'm going to use the equation for capacitance, which is Q equals CV. I'm going to rearrange it to make voltage the subject or potential difference subject. Q is a constant, the charge is stuck on the plate, so I'll rub that out. Capacitance is halved, so that means the voltage will be times, so the potential difference is double. Okay, now for the energy stored in the capacitor, so I'm going to use the equation E equals half Q squared over C. I'm using this one because I know the Q is a constant, the half is a constant, so I can just rub those out. Capacitance, I know what's happening to that, is becoming a half. Again, its inverse is at the bottom there, so the energy stored in the capacitor is going to be times 2. So you might be wondering, why did the energy on the capacitor plate increase? Where did that energy come from? Okay, that comes from the person who's actually pulling the plates apart. If you look at the plates, one is positive and the other one is negative, so they're actually going to be attracting. So in order to pull these two plates apart, the person who's pulling them apart, or whatever is pulling them apart, has to do work, and that's the energy that's being stored in the capacitor. So in this case, the energy stored has doubled. Okay, now for the electric field strength between the plates, we can use this equation, E equals V over D. Now the E here, don't mistake that with energy, that's electric field strength. Okay, so V is the potential difference, and that's becoming, we saw that in part A is being times 2, and the distance between the plates is times 2 as well. So both of those cancel out actually, so the electric field strength does not change, it's unchanged. Example 2, we've got the exact same setup, a parallel plate capacitor with capacitance C charged up to a voltage V, and the charge stored in the capacitor is Q, except this time, while the capacitor remains connected to the cell, the distance between the plates is double, which causes the capacitance to half. So let's visualize what's going on. Close the switch there, let it charge up, and then we're going to pull the plates apart while keeping it connected to the battery, to the cell. Okay, so because it remains in contact with the cell, charge can move off the parallel plates or onto the parallel plates, but what will happen is it will move until the voltage across the capacitor plates is the same as that of the cell. So in this question, it's the potential difference across the capacitor, which is a constant. Okay, so the distance has doubled between the plates and the capacitance has halved. So to figure out what's going to happen to the charge, I'm going to use Q equals CV. Capacitance has halved because we've changed some property of the capacitor distance between the plates. The voltage, the potential difference is V, which is the same as before because it's connected to the same cell. So that means the charge stored is going to be half compared to the initial amount. The energy stored in the capacitor. So for this one, I'm going to use the equation half CV squared. That's because I know half is a constant and V is a constant, so I can rub those out. Capacitance, I know what's going to happen to that. That's going to be half. So the energy stored is going to be half the energy stored before. That's because when you move these capacitor plates apart, we know charge is flowing off the plate, and as the charge flows off the plate, this is going to get dissipated across the resistor as thermal energy. Okay, finally the electric field strength, I'm going to use the equation E equals V over D. Just remind that this is not energy, this is electric field strength, which is potential difference, which is a constant, so rub that out. The distance between the plates is times 2, so that means the electric field strength is going to be half.